Hello everyone, I am Mingyu Lu. Today I'm going to present sensitivity analysis of deep reinforcement learning for sepsis treatment. Reinforcement learning is a machine learning method where an agent will perform an action to interact with an environment. By doing so, it will enter into the next state and receive reward at the same time. By iterating this loop, the agent will learn an optimal policy to maximize the reward that it receives. Recently, there has been a lot of interesting reinforcement learning application in healthcare. However, these RL applications in healthcare also face challenges that the other real-world RL applications face. For example, it's hard to translate high-dimensional continuous state and action into RL settings. Besides, designing a reward function is difficult. Even giving a good reward, we might still be trapped in local optima due to the algorithm restriction. Regardless the issue that I mentioned about, there has been some research shows that these RL applications sometimes can be unstable and hard to reproduce. This is a serious issue in healthcare. If the algorithm that we're using is not robust or stable, then how could the doctor make medical decisions based on it? Early this year, FDA proposed a regulatory framework for AI and machine learning in healthcare, try to call for answers and discussions to this question. What is the appropriate element for regulation of AI and machine learning in healthcare? For people who are not familiar with healthcare, regulation is crucial and essential for all treatment, medication, and even software in this industry. So we try to answer this question, and we consider robustness of reinforcement learning application as one of the elements of that regulation. Only when the algorithm is robust enough that the doctor can trust it and make medical decisions based on it. So we're interested in investigate robustness of reinforcement learning in general. But first, we have to pick a healthcare problem that can apply reinforcement learning algorithm. Thanks to the previous research in deep reinforcement learning in sepsis treatment, we are able to perform our sensitivity analysis based on their work. So sepsis is the body's extreme response to an infection, which will cause multi-organ failure. It is a life-threatening medical emergency and commonly seen in intensive unit care. Maintaining blood pressure is the major goal for sepsis management. Physicians will usually prescribe intravenous fluid and vasopressor to treat the patient. So we can frame this sepsis management into a reinforcement learning problem. Now I'll briefly go through our experimental settings. We try to train a dueling double DQ network to learn sepsis management. In the following slide, I'll just call this agent DQN. For state, we define patient observation, which is 1 hourly laboratory values, including blood pressure, heart rate, and the other vital sign as our state. We then compress it with LSTM to summarize patient history. For the reward, we define the differences between log odds of probability of mortality of 2 consecutive observations as our reward. For action, as I mentioned, intravenous fluid and vasopressor are 2 crucial elements for sepsis management. So we simplify these 2 treatments and discretize it into 5 bins according to their dosage. So here is an example of physician's actions. The y-axis is the dosage of the IV fluid. The x-axis represents the dosage of vasopressor, and the color density represents the frequency of those actions. We specially designed 2 evaluation metrics for the sensitivity analysis. The first one is the action distribution, which is the frequency of each type of action across patient time. The second one is the initiating rate. So we define the initiating rate as the probability of the action taken a non-zero value given that there was no treatment being observed at the previous observation. And now we can start our sensitivity analysis. First, we're interested in the effect of different time window. By time window, I mean the observation frequency within the dataset. Ideally, with infinite data, we prefer shorter time window, because it will improve the confounding adjustment and allow the agent to learn more flexible and dynamic strategies. But in reality, we only have finite data, so this capacity might be detrimental. We investigate the effect of different time window. We train the DQN agent with 4-hourly data and 1-hourly data and to compare the differences in outcome policies. So the upper row is the DQN agent trained with 1-hourly data, and the lower row is the deep reinforcement learning trained with 4-hourly data. As you can see, there is a high variance among different time window. Our analysis shows that DQN agent trained with 4-hourly data is more aggressive compared to 1-hourly agent. It would prescribe higher dosage in both IV fluid and vasopressor compared to 1-hourly DQN agent. It is also more willing to prescribe treatment to patients who are not under treatment at the previous time step.
We also investigate the effect of different state representation. For the state S, it should contain sufficient information to adjust confounding. It should also contain an effect modifier, which is a variable with the property of conditional average effect of an action on future rewards. The state should also satisfy Markov assumption. In reality, to keep a long-term dependency of time series data, people will usually use recurrent neural network to summarize the information hidden in the past. But usually, people will select the recurrent neural network model based on accuracy or the mean square error. But these black box models might have an unexpected effect on the outcome policy. So in this sensitivity analysis, we examine two commonly seen recurrent embedding models. One is GRU, the other one is our baseline LSTM, to investigate the effect on the outcome policy learned by the reinforcement learning agent. Here is the policy learned by the DQN trained with the GRU, and here is our baseline. Our analysis shows that the action distribution of the DQN trained with the GRU embedding is more extreme compared to the one trained with LSTM. We also observe a lower initiating rate in DQN GRU. That being said, the DQN trained with GRU embedding is less willing to give patient treatment given that there was no treatment observed at the previous timestamp. But in some cases, the GRU will prescribe 9 times more IV fluid compared to the LSTM agent. So the recommended policy is totally depending on the embedding models that we choose. We also investigate the effect of different types of reward. Ideally, reward should summarize the long-term utility of patient stay, but the reality is that researchers will usually use short-term reward because it is easier to estimate the association between short-term reward and action. So we would like to see how would this affect the outcome policy. So we design another long-term reward which encodes the improvement of patient status within the intensive unit care and patient survival time after the discharge of intensive unit care. C is the constant that controls the relative weights of these two. Our results shows that the DQN trained with long-term reward will prescribe more IV fluid and vasopressor compared to the DQN agent trained with the short-term reward. In some cases, the vasopressor is constantly given to patients with some constancy. So the agent trained with the long-term reward is much more aggressive compared to the DQN agent trained with the short-term reward. So we must be careful about choosing different types of reward. So the conclusion here is that the choices that we made matters a lot. These seem similar or even trivial factor might have an unexpected or significant effect on the policy. We would never know what would happen on patient if we modified those factors, because it's unethical to perform trials on patients. The least thing we can do is to evaluate the robustness of those policies, and we need new benchmark to do that. We believe that Robustness is the stepping stone to future successful application of reinforcement learning in healthcare. And thank you for your attention. This is my presentation.